Welcome to Visual Algebra Lecture 4.6, Subquotients. When a group arises as a subgroup of another, its subgroup lattice appears at the bottom. When a group arises as a quotient, its subgroup lattice appears at the top. We saw that in the correspondence theorem. In this lecture, we'll revisit the concept of a subquotient, which arises when a familiar subgroup lattice appears in the middle of a bigger lattice. Our last isomorphism theorem, the diamond theorem, describes a certain duality that subquotients have in a subgroup lattice that is easy to spot and visually pleasing. We will see subquotients appear in a few other settings, such as the butterfly lemma of Hans Zassenhaus and involving subgroups called commutators. I will also show you an original visual of the diamond theorem that Pulitzer Prize winning author Doug Hofstadter shared with me, that he calls a pizza diagram. This is going to be fun. Let's get started. Let's do a quick summary of the isomorphism theorems to catch up to where we are right now. The first one we saw was the fundamental homomorphism theorem, and that says that all homomorphic images are quotients. With that knowledge, the natural question to ask is, what do we know about the structure of a quotient? In particular, what are the subgroups? And that's what the correspondence theorem told us. That also has a nice lattice interpretation. And here's an example of that. Here are two groups of order 20, and D5 is a subgroup of one of them, because you can see it sitting at the bottom of the subgroup lattice, but it's a quotient of this other group because it's hanging from the top of a lattice, like a stalactite versus a stalagmite in a cave. At this point, now that we know the subgroup structure of a quotient and which ones are normal, it's natural to ask what happens when we quotient out by one of those normal subgroups. And that's what the fraction theorem told us. And that brings us to the diamond theorem, which is the topic of this lecture. And that describes some sort of duality of subquotients. Now, what does that mean? Let's start by reminding ourselves what a subquotient is, and I will use a familiar example, SL2Z3. Recall that in the previous lecture, we did an application of the correspondence theorem, or just a different interpretation of what it really means. We said that if we take this group and we take the quotient right here, we get A4, then this subgroup of the quotient is the same as a quotient of a subgroup. First taking this subgroup and then taking the quotient right here. And not only are these isomorphic, but they are the same for cosets. This little V4 motif is a subquotient. In category theory, a subquotient is a quotient object of a subobject. So in the land of groups, that's just this thing here, which we said is the same as this by the correspondence theorem. Here is the formal statement of the diamond theorem. Suppose A and B are subgroups of G, and that A normalizes B. Recall what that means. By definition, that means that AB equals BA for all elements A in A. But the important part of that is that it guarantees that AB is an actual subgroup of G. Then the first part says that A intersect B is normal in A, and B is normal in AB. And the second part says that the following quotient groups are isomorphic: AB mod B and A mod A intersect B. Okay, so let's unpack this. This is a little bit algebraically dense, but once we draw the diagram, it becomes a lot more clear. So the fact that AB exists means that we have this natural diamond motif in the subgroup lattice. These normality questions just means that these quotient groups are defined: A mod A intersect B and AB mod B. And then the second part says that these quotient groups are isomorphic. So both of these are subquotients, those motifs of familiar subgroup lattices in the middle of the lattice, and they have the same structure. So this picture is given in many, if not most, algebra books, but it really is the extent that this theorem is visualized in most texts. But I'm going to show you what it really means with some larger examples. Okay, so let's prove these things now. We'll start with the first one. To prove this normality condition, let's take something in A intersect B and conjugate it by A and show that we remain in A intersect B. So let's take something that's in both A and B. I'm going to call it B. We could call it something else if we want to. And an A in A. And then A, B, A inverse is in A, right? Because, maybe I could just say because A, B, and A inverse are in A, and by closure. But we also have to show this is in B. So why is that? A, B, A inverse is in B, and that's because A normalizes B. So we take something in B and conjugate it, it remains in B. So because A normalizes B. So that's the first one, or the first part of the first one. Let's now do the second part, the first one, now. So let's take an element B in subgroup B, and let's call this B1, because I want to take AB in big A times big B. And I want to conjugate B1 by AB and show that I remain inside B. That's what it means for B to be normal. So let's do AB times B1 times AB inverse, and that is AB B1 B inverse A. And now I need to use the fact that that's A inverse. Almost forgot about that. And now I need to use the fact that A normalizes B, which means that every left coset A big B is equal to a right coset B big B A. Well, in other words, this element here, well, it's not quite in here, but because normalizers are subgroups, that also means that A inverse B equals B A inverse, meaning every element that I can write as something in B times A inverse, I can write as something as A inverse times something in B. So this thing here, notice, is in B A inverse, which is A inverse B. So I can write this as A times A inverse times something, let's say B2. So this thing here, something in B times A inverse, I can write it as A inverse times something in B. But look what I have here. I have A times A inverse, which is going to cancel, and now I have B. I have B2. And that's in B, and that's exactly what we had to show. So that's part one. Let's do part two now. And I say let's do part two. I'm going to just sketch it. I will let you fill in the details. This is a good exercise. I typically leave it as homework in my class. So let's define a map. Now you look at this, and this is tailor-made for the fundamental homomorphism theorem. But there's really two ways that we can do things. We can define a map from AB to A mod A intersect B. Let's call this theta, that has kernel equal to B. And if we can do that and show that it's well-defined in homomorphism and onto, then we're done. Or we're going to define a map phi from going the other way, from A to AB mod B, and show that the kernel of this map is A intersect B. Either of these will work, but one of them I think is a little bit easier. You see which one? I think it's harder to notationally describe cosets of A intersect B in A. You know, what do I call an element in here? I guess I could call it, do I call it A or B or G, something like that. So I just think it's easier to talk about elements in here, because let's think about what this A intersect or AB mod B is. That is the set of all cosets of B in AB. So that's cosets of the form A, little a, little b, times big B, where AB is a, big B. But by our boring but useful coset lemma, little b, big B is just equal to B itself. You know, that gets absorbed into there. So this is just little a, B, where A is in A. And that's, I think, just easier to work with than cosets of A intersect B inside of A. Although you can get both to work, and I encourage you to check out the other one. So I will define a map phi from A to A, B mod B. And now, how do you think we should define such a map? I mean, there's not too much we have to work with. So let's take an element, little a, and where are we going to map it to? Which coset? And the cosets look like this, right? Well, what about little a, B? There we go. So there's our map. Why is this a homomorphism? So we don't have to show it's well-defined. Did I say well-defined earlier? No, we don't have to show it's well-defined. Because the domain is not a collection of cosets. You know, there's no equivalence class here. I'm defining it based on an element. So it's a homomorphism. You almost follow your nose. Phi of A1, A2 is A1, A2, B, which by definition is A1B times A2B, which is phi of A1 times phi of A2. So that's why it's a homomorphism. Why is it onto? Let's do that right here. Well, it's onto because if you take anything in here, which we've already said has the form AB, then yes, it has a preimage. So, you know, you can say take any, if you really want to, well, AB big B, which is AB in big A, big B mod B, then phi of A equals A, B, and you're done. Next up, we have to show that the kernel is equal to A intersect B. Remember, we don't have to show it's one-to-one. It's generally not going to be one-to-one because it has a kernel. That's non-trivial. So what is the kernel of phi? The kernel of phi, by definition, is the set of all elements in A, the domain, such that phi of A is the identity element. Now, what is the identity element in AB mod B? Well, which coset is the identity coset? Well, that's going to be B. So this is the set of all A in big A, such that phi of A is AB equals B. And that is the set of all elements A, little a in big A, such that, remember what, by our boring but useful coset lemma, that just means that A is in B. And what am I describing? That is the set of all elements in A and B, so that is A intersect B. And that is the proof. I said a sketch. In my lecture in class, I don't do it as, I sketch just what you have to do, and then I leave it as homework, but here I guess I did the whole thing. Oh well. Let me do a quick corollary. Let's say that G is a finite group, and that A and B are subgroups of G with one normalizing the other. Doesn't matter which one. Then the size of AB is the size of A times the size of B over the size of A intersect B. Now this is something that we've actually proven in an earlier lecture more generally. That was a lecture on double cosets. Even if AB isn't a group, then AB will be a double coset, and we got this relation more generally. But this falls out right from the diamond theorem, and let's see why that is. So that is, if we move the order B over to the left-hand side, that is the same thing as saying size of AB over the size of B is the size of A, or the order A, over the order of A intersect B. And now, you see why that's true? Well, if these groups are isomorphic, then this left-hand side is the size of AB mod B, and this right-hand side, I shouldn't say equal, I shouldn't say isomorphic, I should say equal, is equal to A mod A intersect B. One last comment. Do you see why I said if either one of these normalizes the other? So if A normalizes B, we have this picture like here, but if B normalizes A, then we have a similar picture like this, and it doesn't matter which one. In both cases, we can conclude this equality. Okay, now I want to give you some better visuals than these little dinky motifs that are standard for the diamond theorem. First up is the abelian group Z2 cross Z6, and consider the following subgroups A and B. I think it's better to just write them on the lattice. So A is this Klein 4 subgroup, and B is this Z3 subgroup. Then A intersect B is trivial. A times B is this entire group. So this is AB. This is A intersect B. And the diamond theorem just says that this quotient, which is V4, is isomorphic to this subgroup, which is also V4. And the fact that the subgroup lattice of V4 is diamond-shaped is purely coincidental, but it's a nice touch. Here's our next example. This is a semi-direct product of Q8 with C9. And if A is Q8 and B is C6, so both of these are normal because they are the unique subgroup of their order. Then they intersect in C2 and they generate Q8 cross C3, and the diamond theorem says that this subquotient, this V4, is isomorphic to this subquotient. Well, also because they're both normal, they both normalize each other, that also says that this subquotient, which is C3, is isomorphic to that subquotient. This is not the last that we will see of this lattice. We'll see it at the end of this lecture, but also again in chapter 6. Hopefully, with this example and the previous one, you can see what I mean when I say duality of subquotients. It's not a precise thing, but the idea is that a lot of times these subquotients come in pairs along these little diamond motifs. And this is my own term. I haven't heard it elsewhere. I actually haven't heard other people talk about the diamond theorem in terms of subquotients, but I think it's a nice little cherry on top after talking about the correspondence theorem and the fraction theorem being subgroups of quotients and quotients of quotients. Now we have quotients of subgroups. At this point, I have a fun story to tell you about. This is a picture due to Pulitzer Prize winning author Doug Hofstadter. You might know him as the author of Gödel, Escher, Bach, which was published in 1979. And when I was in college in the late 90s, early 2000s, it was a cult classic, and it still is among certain circles, but it seems like the younger generations don't know it as well as my generation did. So I'm hoping it will have a resurgence at some point, but it's a fantastic book about math, art, and music. It's very fun and very playful. I encourage you to check it out. But Anyways, if you watch the Chapter 0 lectures in this series, you know that Doug Hofstadter taught a visual group theory and Gabler theory course 3 times at Indiana University in the early 2000s. And in one of those classes was Nathan Carter, who went on to write the book Visual Group Theory in 2009. And that's the year that I met him at MathFest in Portland. And I started teaching algebra that way. And then the rest is history. So Nathan introduced me to Doug over email, and we've emailed a lot back and forth, a lot of times at 2 in the morning, both of us. And he made some comment about visuals he used and pizza diagrams, as if I'm supposed to know what that was. And I said, what's a pizza diagram? And so he said, oh, let me show you this. And he sent me some hand-drawn pictures. And he said something like, this is something that is not in books, but I think anyone who understands the diamond theorem kind of has to have in their mind in some sense. And I was like, well, I don't have this picture in my mind, but I have other pictures like the ones that I already showed you. So I think the moral is that anyone who really understands this stuff has to have something in their mind, some sort of mental picture that's beyond what is typically given in the textbooks, which is unfortunate because not everybody develops those or learns how to cultivate those. So this thing, I don't think I should have to explain why it's called a pizza diagram, but it's kind of a schematic that you have 2 groups. One of them is A, and it's given by like this pizza, and B is this pizza slice. So the intersection is this smaller pizza slice, A intersect B. And the diamond theorem says that, so if you think of like these slices as, this slice as like a coset, so AB mod B, first of all, A times B is this big pizza. So AB mod B is saying, let's take the big pizza, but mod out by slices. So the elements of this quotient group are the actual slices of the big pizza. And here you got a group of, say, size 8. If you take this drawing as to be 8 slices of pizza, and this set of 8 pizza slices is isomorphic to A mod A intersect B, which is the smaller pizza mod the smaller pizza slice. So this is the group of small pizza slices, and this one is the group of large pizza slices, and they have the same algebraic structure. And that's the diamond theorem via pizza diagrams. So I thought you might get a kick out of this, and I think Doug will certainly get a kick out of this being in this video and also in my book. And if you enjoyed this example in this story, then go on Amazon or wherever and go buy Gödel, Escher, Bach. Let's make it popular again, give it a resurgence that it deserves. If the TV show Friends can come back among the next generation, well, so can this. I want to now do an application of the diamond theorem to permutation groups. This fact is something that I probably mentioned in chapter 2, but if I did, we didn't have a good proof then, and there is a very notationally cumbersome proof that you can find in the exercises in my book. But there's a very clean proof once we have the diamond theorem under our belt. And this result is that suppose H is a subgroup of Sn that is not contained in An. That means that it's a subgroup that has at least one odd permutation in it. Then exactly half of the permutations in H are even and half are odd. This is something that you should expect or hope for morally, but it is indeed true. So how does this relate to the diamond theorem? What if I show you this picture? Does that help? So here's Sn. It's not a full subgroup lattice, it's just a part of it. Here's An, here's H, and then the intersection, by definition, are the permutations in H that are in An, meaning the even permutations in H. And by the diamond theorem, well, first of all, the assumptions of the diamond theorem are satisfied because this is normal. So that means that the product of these two is the group Sn. So Sn mod An is H mod H intersect An. And really the important thing is that this has index 2 in Sn. And so this has index 2 in H. Can we write that up formally? I think I basically talked our way through it, but it suffices to show that H, or the index of H intersect AN in H is 2. Because that just means that, I mean, if I draw a picture of that, if this is H, and this is H intersect AN, then these are the even permutations, and things that are not in here are the odd ones. Okay, so equivalently, H mod H intersect AN is isomorphic to C2. But since H is not contained in AN, H times AN is bigger than AN. It's bigger and not equal to it. So that means that H AN is equal to Sn. So then, by the diamond theorem, H mod H intersect AN is H AN over AN, which is Sn over AN, which is isomorphic to C2. You probably didn't need me to actually write this, did you? It's all in the picture. I hope it hasn't been lost on you that thus far in this video, we've had the diamond theorem, pizza diagrams, and now the butterfly lemma. So what is this one all about? First of all, this is pretty technical. I don't think it should be clear algebraically what it means. And it's called a lemma because on its own, it's not all that interesting, but it's used as a tool to prove some bigger results, in particular the Jordan-Holder theorem, which we'll see in chapter 6, though I won't use this. So why am I showing this to you? Well, partially for amusement. I'm not going to go through and try to explain what this means, but I will show you a picture. And this should make it clear both what it means and also why it's called the butterfly lemma. So this is a subgroup lattice, and it just says that if you have groups A and B, notice how they intersect here, and you have M and N, which are normal in A and B. So notice how this group here is A intersect N, or let's see, so A intersect N is down here, and that times M is up here. This group is B intersect M. This is just good practice to do with subgroup lattices. B intersect M is down here, times N over here is here. And the idea is that this quotient, or the subquotient, is isomorphic to that one. And the way this is proven is by showing that both of them, or really just either one of them, by symmetry, is isomorphic to this one right here. And you can check out my book for proof of this. It's not too hard. It's a little notationally messy, and it basically follows from the diamond theorem. And this kind of looks like maybe a fighter jet or a butterfly doing a nosedive, but if you turn it upside down, so down here the group G is in the bottom, and you take some artistic liberties, you do get something that looks like a butterfly. So sometimes this is called the Zassenhaus lemma. I think you should call it the butterfly lemma. And I hope that Zassenhaus, who is a 20th century German mathematician, would agree with that opinion. At this point in my class, students are finally getting used to describing and analyzing subgroups based on their lattices and in particular quotients. And I like to put in this topic of commutators as an example to illustrate this. Now, this is not needed. It is going to be revisited in chapter 6. It's a big, important topic there. But that's not in Algebra 1, so most students are not going to see it, and I think it's worth seeing this at some point. To motivate it, we've seen how to divide the integers by the multiples of 12. In other words, take a quotient of the integers by 12z, and thereby forcing all multiples of 12 to be 0. We do this in our everyday life when we tell time. This is one way to construct the integers mod 12, and we get the isomorphism via the fundamental homomorphism theorem. Now, suppose G is non-abelian. We'd like to divide G by its non-abelian parts, making them 0, and leaving only abelian parts in the resulting quotient. So here we want to force multiples of 12 to be 0, and here we want to force anything non-abelian in the group to be 0. A commutator is an element of the form A, B, A inverse, B inverse, and since G is non-abelian, there are non-identity commutators. In other words, there are products of the form A, B, A inverse, B inverse that are not equal to the identity. In terms of the subgroup lattice, if these are generators, then you'll see paths like this: red, blue, backwards red, backwards blue, that do not end up to where you started with. And if G is not abelian, then there has to be at least some pair of generators that do not commute. So you will see this motif. Whereas if you have an abelian group, you'll see motifs like this throughout. So in this case, let's define the set C to be the set of all commutators. And if G is non-abelian, then this will have more than just the identity element. This is always going to be non-empty because it will always contain at least the identity. The commutator subgroup, denoted G prime of G, is just the subgroup generated by these commutators. Just like up here, if we wanted to force the multiples of 12 to be 0, we quotient out by it. We are going to soon quotient out by this subgroup, and whatever remains is going to be abelian. It's a not hard exercise to show that the commutator subgroup is normal in G, and that the quotient is indeed abelian. Let me say a bit about how you show it's normal. So I'll let you finish the details. But for normality, you take a commutator. It suffices to just take a generator of this. You don't have to take any word in this. You should notice that if the product of two commutators is generally not going to be a commutator. So you take something like this, and what you want to show is that any conjugate of this, C or GC G inverse, is in the commutator subgroup, but this also is not necessarily a commutator. If you stick a G here and a G inverse, it looks like a commutator, but it's not one. So what can you do? Well, we know that GC G inverse C inverse is a commutator, right? And we know that this is closed. It's a subgroup, so it's closed under multiplication. So if we multiply this element times C, so we know this is in here and C is in here. So GC G inverse C inverse times C is in there as well. And that's what we wanted to show was in G prime. So that's why it's normal. And why is it abelian? Well, I think the easiest way to say it is if you have cosets A G prime, B G prime times A G prime inverse, B G prime inverse. So let's take a commutator in here. Notice that x, y equals yx for all group elements in a group, if and only if x, y, x inverse, y inverse is the identity for all x and y. So if you just take a commutator in the quotient, by definition, this is A, B, A inverse, B inverse, G prime, and this, by definition, is in G prime. So by our boring but useful coset lemma, this is equal to the identity element G prime. The quotient of G by its commutator subgroup is called the abelianization of G, and we will study this more in chapter 6. The commutator subgroup, in some sense, is the smallest normal subgroup, n of G, such that G mod n is abelian. In other words, it is the smallest subgroup that we can quotient out by and get an abelian quotient. Equivalently, this quotient is the largest abelian quotient of G. So note that in general, if we have a group G, what I'm claiming is that G prime, so we know that this is abelian. And this is, in some sense, the smallest subgroup whose quotient gives an abelian group. There might be other ones. There might be H and K above here that also give abelian. And that's something we can actually prove, is that any other quotient by something larger than G prime will be abelian. You can do that right by the fraction theorem, because if this is abelian, then every quotient of an abelian group is abelian, and apply the fraction theorem. So when I say that G would be the largest subquotient, I mean, these are all the things that give an abelian quotient. This is the smallest one right here. And therefore, this resulting quotient is the largest quotient. The smallest such quotient would be G mod G, which is trivial. So this is something we'll do in chapter 6. And it's also not obvious that there is a unique smallest G prime. How do you know that there's not some other G1 prime, whose quotient also gives, and let me use red here, that also gives an abelian quotient? And well, the idea is if there is one, then their intersection would have to be as well. And that's basically why there's a unique one. So if there's two of them, then their intersection would also have that property. This can be formalized via something called a universal property of commutator subgroups. Chapter 7 is all about universal properties. So I'm going to really hold off till chapter 6 when we study commutator subgroups, and chapter 7 when we formalize them. But let me just go through this for anyone interested. The way you would formalize this is, suppose, what do I mean by the largest abelian quotients? Because you can't necessarily compare two different quotients. But here's how you do it. Suppose you have a homomorphism from G to some abelian group A. Then the idea is that there is a unique homomorphism from the abelianization such that F is just the composition of this quotient and then H. So what that really means, and again, I'm not going to spend much time on this here. I'll refer you to chapter 6 and chapter 7, especially chapter 7, is that if you have, so this is an abelian quotient, and if you have, and this here is G mod G prime, and if you have anything else in here, say, if you have any other abelian quotient, say this is A, then you can form this quotient by first chopping off at, taking the quotient at G prime, and then taking the quotient at H. So that's really just an application of the fraction theorem. So that's, again, one reason why I like to put this in here, just to kind of give you some hints as to what's coming next and how this involves the isomorphism theorem. We say that this map factors through the abelianization. The take-home message that I want you to get from commutators and abelianization is that we can often, if not usually, spot these things by inspection in the subgroup lattice. And I want to show you 4 examples. So for all of these, this is A4 alternating group, the dicyclic group, dihedral group, and the semi-abelian group. Again, if you have not watched my earlier lectures, like in chapter 2, you might not know what these groups are. So please do. So first of all, let me just circle all normal subgroups. So in all of these groups. And then here, remember, all of these are normal except 2 of them. So for each of these, you can quotient out by it, and you can say, what is that quotient? And this is good practice for you to do. So this quotient you should recognize as D3. This quotient is C3. This quotient, of course, is V4. This quotient here is C4 cross C2. This quotient here is also C4. And the idea is that the commutator subgroup is the smallest subgroup whose quotient is abelian. So let's start with A4. If you quotient out by this, you get A4, that's non-abelian. So the smallest thing that gives you an abelian quotient is this one right here. And the abelianization, A4 prime, is isomorphic to C3. Up here, dic 6 mod r cubed, well, this is D3, that's non-abelian, but dic 6 mod r squared, this is the commutator subgroup, and this is, oh, sorry, I said A4, I meant A4 mod A4 prime. So this is dic 6 mod dic 6 prime is isomorphic to C4, and because you can recognize that lattice of C4 right there. So over here, you can see by inspection that this is the smallest, this is D4 prime, this is the smallest subgroup that gives an abelian quotient, and so this is D4 mod D4 prime, which is isomorphic to V4. And then over here, it's tempting to say, like, oh, look, this gives us a V4 quotient, but hey, look, this one also gives a C4 quotient. Remember what I said, there's a unique minimal one, so if you have two of them, look below, and indeed, this subgroup here is SA8 prime, and this quotient, SA8 mod SA8 prime, is isomorphic to C4 cross C2. So once again, you don't need to know about commutators and abelianizations, but at this point, I think it's really good to practice getting used to taking a quotient and also just being familiar and spotting our familiar subgroup lattices in the bigger subgroup lattices. That's something that I definitely want my students to do on exams. Sometimes I do put an abelianization question on it in Algebra 1, but even if I don't, it's a great way to study for this class in general. I want to finish by saying one more thing about commutator subgroups and what we will do in Chapter 6 and tie it back to subquotients. This is a group that we saw in the beginning of the lecture, the semi-direct product of Q8 and C9. So in Chapter 6, we will start up here and say, okay, what happens when you take the commutator subgroup? And you look down here. Well, let me circle the normal subgroups. So all of these things are normal. And this mod that, well, ooh, that's recognize that? That's A4. It's got index 12, so the quotient has order 12. Hopefully you can recognize this motif by now. So that's too far down. What about this? This quotient is C3, but this quotient is actually C9. So this is G mod G prime is isomorphic to C9. And then we can iterate this process of taking commutators. This is a group, Q8. It has a commutator subgroup. Let's call it G double prime. And now this subquotient, G prime mod G double prime, is isomorphic to, you recognize it? You should, V4. This is now a group. We can iterate, we can take its commutator subgroup. Well, it's abelian, so its commutator subgroup is the trivial group. So G double prime mod G triple prime is isomorphic to C2. So this is something we can do for any group. We may get down to the bottom, we may not. And if we get down to the bottom, it's called solvable. And that has something to do strongly with solvability of polynomials by radicals. And that's what Galois theory is all about. And that's the topic in Chapter 11. And that's just one of the most beautiful pieces of algebra in this course. And I know that's saying a lot because I'm a little biased, but I think there's been a lot of beautiful things up until now. And there will be even more beautiful things to come. But I like this example because, again, it gets you practicing the isomorphism theorem, seeing these motifs. And it's also an example, this particular one, commutator series, is an example of subquotients in the subgroup lattice. Okay, so that's a great place to stop. And that finishes the isomorphism theorems. Next up, we will look at automorphisms, and you should be familiar about those from when we saw semi-direct products in Chapter 2, we talked about rewirings of Cayley graphs. Now that we finally have homomorphisms formalized, we can talk about automorphisms as homomorphisms or isomorphisms from a group to itself. And we can do that topic properly. We can also we'll also learn about inner versus outer automorphisms and the outer automorphism group. And we'll see an incredible fact that physicist and mathematician John Baez calls a wrinkle in the mathematical universe. So there's a lot to look forward to. Stay with us.